Hello everyone, welcome back. This video will be taking a look at limits of sequences. So before we start going into limits, I want you guys to note that limits are really important. In fact, calculus as a whole is all about limits and real analysis, of course, which is just a fancy word for calculus, is all just about limits. So first we're going to take a look at sequential limits, i.e. the limits of sequences. So before we take a look at before we go into the definition of a limit, let's take a look at what really is a sequence. So the formal definition of a sequence is a function with domain as the natural numbers and the codomain as the real numbers. Well, what does that mean? Well, since a function is anything that takes in input and spits out some output, so a sequence is a function which takes in the real numbers, which takes in the natural numbers and spits out the real numbers. So if you guys remember the Archimedean principle that we did in a previous video, well, that Archimedean principle is really helpful for us in sequences because it relates natural numbers and real numbers, and we need that for the limits of sequences. So let's take a look at what this actually means. So a sequence is any set of numbers in any order with the the domain as a natural number. So they take in the natural numbers. So if we draw it in x-axis, y-axis form, the x-axis to the left of 0 does not exist. It's not possible because the natural numbers start from 0 or sometimes from 1. So therefore when we're doing sequences, we'll always be just drawing this way. We won't be drawing this. So we will be so but they have the codomain as the real numbers, so they can go about, so they can be, so the x values can be to only positive, but the y values can range all the way from infinity to negative infinity. And I want you guys to note that a sequence can be any numbers. For example, this random digits. This is a sequence of numbers. Another one is, let's take a look at this. And this is a sequence. And this, sorry, we shouldn't draw the x-axis here. And this is a sequence. And so is this. So a sequence is any set of numbers, It's not a must that they have to be ordered. They can go all the way to positive infinity, like all the way, not to positive infinity, right? They can go all the way to, for example, a million and drop back to -1 and continue this way and go back again up. So a sequence is any set of numbers with the domain as the natural numbers and the codomain where they spit out is actually the real numbers. So let's take a look at the definition of limits for sequences. So L is a limit. So L is a limit of a sequence if for all epsilon greater than 0 there exists an n in the natural numbers such that an minus L is less than epsilon for all n greater than n. Well, what the hell does that mean? So before we dive into the definition, note that sequences will always be from now on be written in this way: an or bn or cn or dn. All these are sequences. So we're told that L is a limit of a sequence if for all epsilon greater than 0. So what is epsilon? So epsilon is basically an arrow. Let's look at this visually to see what's really happening here. So consider this sequence, which is going gradually and then it levels off, and this as L, or I do it a 4 over there, and epsilon. Right, now we're told there exists an n in the natural numbers such that an minus L is less than epsilon. So an minus L less than epsilon is basically, so an is a term in the sequence, it's a sequence itself. So an minus L, modulus of an minus L less than epsilon can be written as, for example, as we did in the previous video, there are two cases, so can be written as this way, and this can be written as L plus epsilon, L minus epsilon. So let's put this in the graph right here. L plus epsilon, L minus epsilon. So we're dissecting the definition right here. So it says there exists an n in the natural numbers such that this is true for all n. What's this n? Remember, this is a sequence an, so this n represents this n. So a sequence basically goes like a1, a2, a3, a4, a5. So for some n, for example 5, and which is greater than some other n, for example 4.5, that this is true, an minus L is less than epsilon. So what does this mean? So for example, in this sequence which I've drawn here, we'll put this as n. So what it's saying is, after some time, if the limit exists, limit L is a limit of a sequence, if after some time, so this is the capital N right here, after some time, all n, for example, this is a 50 and n right here is 49, and note that these are it's in the natural numbers. So for n, so n right here, this is n greater than 50, an minus L is less than epsilon. That means all the terms in the sequence, the distance between this term, for example term 51, and L is less than epsilon. Epsilon is just an arbitrary number. What it basically, it's a Greek letter for E. And why did we choose E? Because E is like the error, it's like really small. Epsilon, note that always epsilon is really small, really small. We're working with for example 0 0.1, 0 0.001, and 0 0.000001. Epsilon is really small. So what the definition is basically saying is, for a sequence, the limit, if a sequence has a limit, then after some time, after some n, after some capital N, all the terms in the sequence, for example a50, a51, a52, a53, a100, all the terms of the sequence after the capital N, always after the capital N, all of them are all in this tube right here, L minus, in this tube L minus epsilon, L plus epsilon, in this tube, or in this hole, or in this gap, or in this pipe right here, all of the terms of the sequence are in this tube. So what it's basically saying is, the any term of the sequence, the distance between this term, for example, and L, which is, so the distance is denoted by an minus L. So this term is a an, maybe it's a53, we do not know that. So this term right here is a an, it's a term of the sequence. So the distance between this and this, which is written as an minus L, and we don't know, it's sometimes positive and sometimes negative. For example, if the term was right here, then an minus L would be positive. But since in this case L is bigger than an, as we see from the graph, it's negative, so that's why we use the modulus sign. This distance between this point, this term in the sequence, and L, this vertical distance, is less than epsilon. And what did we say epsilon is? It's this distance right here from L to L minus epsilon. It's this distance. So L is the center of the tube, and epsilon and L plus epsilon and L minus epsilon are the walls of the tube. So this is L minus. So these are the walls of the tube, and the center of the tube is L. So the definition is basically saying after some time, and this center of the tube is the limit of the sequence, because eventually all the terms end up being very very close to it or even equal to it. Eventually all the terms are equal to the limit. It therefore the sequence is tending towards the limit. So it doesn't matter, for example, the consider this sequence right here is going up and down, up and down, up and down. But it doesn't matter. After some time, eventually, later on, after millions and trillions of these cycles, it will eventually be end up being in the, it'll end up being in this tube. So that's what basically the definition of a limit. So let me explain it once more with a neater looking graph to make this more clear. So if we have a sequence this way, and if we have L this way, and if we have epsilon, L plus epsilon, L minus epsilon, it doesn't matter what the sequence does at the start. What the sequence does at the start is just pure noise. It doesn't matter to us what the sequence does at the start. It can go up, it can go down, it can go up, down, it can stay in the tube for some time, it can come off the tube and go back in the tube and stay in the tube for some time. But eventually, after it goes back up, but eventually, if the limit of the sequence exists, there exists an n such that after this n, all the terms in the sequence, eventually, all the terms in the sequence end up being in the tube. They all stay in the tube and never get off this tube where the center is the L and the walls of the tube are L plus epsilon and L minus epsilon. It doesn't really matter what the sequence does at the start. It can stay in the tube just like as it did here. It can come off the tube, it can go back to the tube and stay in the tube. But eventually, after some n, there always exists some n, some capital N, such that all terms of the sequence, all n greater than n, where the small n represents terms in the sequence. For example, n right here is 1000. Then for all n greater than this n, this capital N, for example, a 1001, a 1002, all of them till a 1 trillion, till a 1 zillion, all of them they stay in this tube and never get off this tube. So let's take a look at how epsilon and n relate. So again, consider this sequence. So this is the L. L is the limit of the sequence. So eventually all terms of the sequence tend towards L. They're very, very, very close to L. The distance between a term and L is always less than epsilon, where epsilon is really, really, really small. For example, epsilon is 0.1000 zeros and then a 1. So the distance between this term and this term an minus L is less than epsilon, and we know epsilon is always really 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 small. So we can say that these two are almost equal to each other. Therefore the sequence tends to this limit. So let's take a look at how epsilon and n relate. So I'm going to take a rather large epsilon, maybe 0.1. So this is a L plus epsilon, this is a L minus epsilon. So for this epsilon 1, the terms of the sequence, first they do some nonsense, they do some noise. Whatever happens at the start of sequence really doesn't matter. What we really care is what happens at the end of the sequence. Eventually, after millions and millions of terms, all we care is what happens at the end of the sequence. What happens when the sequence tends towards infinity? What really happens when it goes far and far? What really happens at the start doesn't really matter to us. What happens, for example, in the starting 1000 or starting 2000, starting 3000 terms of the sequence doesn't matter. If the sequence can do whatever it wants, it doesn't really matter to us what it does. What we really care about is what happens at the end of the sequence. So, for example, this sequence does some strange things at the start, but then it 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 ends up being in the tube. It ends up being in this tube. So for this epsilon, it ends up being in this tube. Then let me do it this way. Right, bear with me right here. Just give me a moment. It ends up going this way. It ends up becoming closer and closer to L. So for this epsilon, which was a rather large epsilon right here, this large epsilon requires n to be quite small. After this quite small, this n is relatively small. After this quite small n, all the terms of the sequence and are end up being in the tube. For all n greater than this n, this n right here, all the terms of the sequence which are greater than this n, all the terms of the sequence are in the tube. But if we make epsilon to be smaller, if we choose the tube to be smaller right here, if we choose the tube to be smaller as L plus epsilon L, I'm sorry about that, L minus epsilon. So if we choose the tube to be smaller, if we decrease the length of the tube, we notice that these terms, I hope you're seeing this, these terms are no longer in the tube. Let me just do a solid line for this tube instead of a dotted one. We notice that these terms are no longer in the tube. They are in the tube for some time, but then they go out of the tube, and then they come back in the tube, and they go out of the tube. But then after some time, even these terms, even after some time, after some n, even these terms are end up being in this even smaller tube. So for this, we require an even larger n. We require a larger n for this. So as epsilon gets smaller and smaller, we need to go further along in the sequence to find this capital N, for which all small n, and note that this small n are the terms in the sequence. Note that the sequence is denoted, I'm sorry about that. The sequence is denoted as an, where this small n represent terms of the sequence. So for this small n greater than this capital N, for example, n right here is 1 trillion. So for all this small n, 1 trillion 1 trillion plus 1. For all this 1 trillion plus 2, this is 1 trillion plus 2, this term is 1 trillion plus 3, plus 4, plus 5. So for all these small n's, the terms of the sequence end up being in this smaller tube. And if we make the tube even smaller, such as this way, we need to go further along in the sequence to find an n where all the terms are eventually in the smaller tube, because we notice right here that if you make the epsilon to be even smaller, as we did right now, as we make the epsilon to be even smaller, we notice that these terms, I hope you guys are seeing these terms. Check out this yellow spot right here. This yellow spot or yellow term, this term is out of this smaller tube, this smaller tube. So if we make the tube to be even smaller, we need to go even further along the sequence to find another capital N for which all small n, where small n denotes the terms in the sequence for which all small n are greater than n. So as epsilon gets smaller and smaller, capital N becomes larger and larger. So I'm going to say this one more time. We go for a different color right there. So when we started with a quite large epsilon, as we started here, L plus epsilon 1, we just needed a small n to do the job, after which all terms of the sequence, this graph is a little messy here. I hope you can still see it, but we just needed a small n for which these terms are not there, but we just needed a small n after which all these terms are in this tube, in this blue tube right here. But when we made the epsilon to be even smaller, as you can see with this pink one, this pink tube right here, which I'm drawing on, we needed a larger n, we needed this n. And when we made the tube even smaller, some terms were coming out of this even smaller tube, and therefore we needed an even larger n. We needed this n right here. We needed this n to guarantee us that after this capital N, all the terms of the sequence are in the tube. So when epsilon gets smaller, n, capital N, becomes bigger. So I want you guys to note that what happens at the start of the sequence doesn't really matter. What matters is eventually at the end, after some time, all the terms of the sequence are close to L. If at the start of the sequence, some terms will be close to L, some terms will be far apart from L. But at the end of the sequence, near the end of the sequence, all the terms of the sequence should be close to L. The distance between an, the term of the sequence, and L should be less than epsilon. So I hope you guys enjoyed this video. See you next time.